interested in killing. I just want to prove how bad your kicks are.
All right. So, today's lecture is going to be a little bit shorter. I'm going to basically go over a couple more examples of the PageRank stuff, and I'm going to start with some of the basics of. Oh, actually, it might take the full time. It might take about an hour. But I'm going to lay down the basics of singular value decomposition stuff. And then what I'm going to do is over the weekend I'm going to upload some supplemental lectures slash me working out some problems that you guys can watch whenever you feel like it. And that is so that's going to form like a kind of a nice bunch of problems that I've worked out in addition to the examples. And then what I thought I might do is assign a few problems from some of the sections in the online notes. And then next week, either during the Tuesday, Thursday live streams or some other time that I haven't decided, but I'll post that over the weekend. I will conduct like a problem session where you all can ask me questions and I'll work through some of them, or I can just work through a bunch of examples. So I think that makes sense for this class to do a bunch of that. Of course, a lot of stuff that involves MATLAB, I'm working with getting a screen capture to work so that you guys can see my screen at the same time, so that basically I can go to both of these things, so that I might use that to do some MATLAB stuff. Otherwise, I'm just going to refer to you to the MATLAB blocks of code in the online notes. So I'm still working out the kinks of that. But anyway, last time in our discussion of PageRank, so just a quick review. So the way that the PageRank algorithm works is the following. So we have, last time I used this example. So our internet consists of just these 4 web pages, and the arrows are indicating the directions that the links are pointing. So the Google PageRank algorithm is the following. So you assume a random web server starts at some page. If a page has outbound links, then there's an 85% chance that the random web server chooses one of the links, and each choice is equally likely. There's a 15% chance that the random web server chooses a page at random from all possible pages. And if the page has no outbound links, then there's a 100% chance that the random web server chooses a page at random from all possible pages. And the random web server will continue to do this forever. Okay, so that was the basis of the process, and we saw that applying to this particular example, when I formed the matrix T, that of course turns out to be a transition matrix. When I formed this matrix T, the way that I did this is I have I'm off the page. So the way that I did this is the following. So there's my example. Here's my 2 matrices. So here's the matrix that is telling me the 15% of the time where I'm choosing at random, and the right matrix here is the 85% of the time that I'm not. Right, and so this bit is easy to come up with. Right, this matrix always looks something like this, but in this right matrix, coming up with these entries is the bit that requires a little bit of thinking. So just to remind you where these entries came from, so I had this entire row was zeros, is maybe the first thing you look at. What does that mean? Well, what that means is that, so this entire row is associated to web page 1, and what it means is that no pages link to web page 1. And you can just check really quickly, they don't. So since no pages link to web page 1, all these entries are zeros. Okay, so moving to the second row is corresponding to web page 2. Web page 2 does get linked to. It gets linked to by page 1. Okay, now why is there a 1/2 here? So if you remember, the reason there's a 1/2 here is because there are 2 web pages that page 1 links to. Page 1 links to page 2 and page 3. Okay, and so the way that this entry is determined is one of those links goes to page 2, and we're in the row that is determined by page 2. And there are 2 possible choices there. Right, so the probability that page 2 gets chosen is 1 and 2. Right, that's 1/2. All right, and so that's why there's a 1/2 there. No other page links to page 2, so all the remaining entries are 0. Okay, and just refreshing your memory on all these, if I look at row 3, page 3 gets linked to a bunch, right? It gets linked to 3 times. So it gets linked to by page 1. As we saw before, page 1 also links to page 2, so there's 2 possible linkings from page 1. So 2 total, and only one of those goes to page 3, so that's 1 and 2. Next, I have a link here from page 2, and that's the only outbound link that page 2 has, right? So that single link, and so that's a 1 because it's 1 outbound link, and there's 1 total outbound link, so it's 1/1, or 1 here. Page 3 doesn't link to itself, so that's a 0. And page 4 links to page 3, and it's the only page that it links to, so again, a 1 here. Okay. Lastly, for the row associated to page 4, page 4 only gets linked to by a single page, and that's page 3. And that's why I have an entry here in the third column. Okay, so that's how it goes. So you have a transition matrix here, and then the way that you actually compute the page rank of each of these pages is to seek out the steady state vector, which we did in the previous chapter, in chapter 7, where we dealt with Markov chains. That's where we talked about how to find steady state vector. So the exact same process for doing that applies here. And so what we got was steady state vector here. This gave us page rank. And at the end, last time, I did an analysis of what it meant to what each of those page rank numbers meant, right? Okay. So now let's do another example. And in this example, I'm going to have one of these. I'm going to have an example of an internet where you have a web page with no outbound links. Okay, so remember, this was one of the reasons why our completely naive algorithm was bad, was because it had no way of dealing with a page with no outbound links. So here's an example. So consider the internet given as follows. Again, only consisting of 4 web pages. So here's page 3, here's page 4, here's page 1, and here's page 2. Okay, and so the diagram looks like the following. So page 1 links to both page 3 and page 2. Page 2 links to both page 3 and page 4. Page 4 links to page 2. Make sure I got everything. Yes, that is everything. So note, page 3 has no outbound links. And so note, piece of 3 has no outbound links. Okay, well, maybe that's not that clear. There we go. Okay. So, how do I handle this? So I want to write out my transition matrix. So my transition matrix, again, this left term is actually easy to determine. So this left term is my matrix full of 1s. Why is there a 4 there? Here, so this 0.15, you know where that comes from. It's because this is taking care of the 15% of the time that a random web page is visited from some source page. And this 4 is because there's 4 total pages, right? So this would be an n if it was an n page internet, and this matrix would be an n by n matrix instead of a 4 by 4. Okay, and I'll mention that again in a bit. So then this 85% case, which is kind of the meat of these problems, some 4 by 4 matrix here. How do I determine the entry? So as before, I look at the first row. The first row is associated with page 1. And I ask, does page 1 link to itself? No, so that's a 0. Does page 1 get linked to by page 2? No, so that's also a 0. Does page 1 get linked to by page 3? Well, looking at the diagram, it seems like the answer is no. It seems like I should put a 0 in here, right? But I'm not going to do that. Why not? So remember in the where did I have it? Yeah, in the description of the PageRank algorithm, we had a specific entry here that dealt with the case where you had no outbound links. So if a page had no outbound links, there's a 100% chance that the random web surfer chooses a page at random from all possible pages. So what that means is coming here when I'm splitting into so 15% of the time that's true regardless of what page I'm on, whether I have outbound links or not. But for pages that have outbound links, 85% of the time they're going to use one of those outbound links. They're not going to choose randomly. But for a page with no outbound links, even in that 85% of the time, they are going to choose randomly. And so, yes, page 1 technically is linked to here by page 3. It's linked to in this 85% case when it gets randomly chosen. And it gets randomly chosen from 4 total pages. So the entry here is 1/4. Okay, so that's where this 1/4 comes from. Now you might already notice that I'm going to be able to fill out 1/4 down this entire column for that exact same reason. But so maybe you could say, go ahead and fill those in, because the reasoning is exactly the same for all of these pages. Even though page 3 technically doesn't link to them according to the diagram, because page 3 has no outbound links and because 100% of the time under this algorithm it means that there's a random choice, I get 1/4 in this entire column. Okay, so every single entry is 1/4. Now, lastly, for page 1, does page 4 link to page 1 in this 85% case? The answer is no, so that's a 0. Okay, so entry by entry, page 2. Page 2 gets linked to by page 1. So it does get linked to by page 1. And page 1 links to 2 total pages, so the entry here is 1/2. Okay. Page 2 doesn't link to itself, so that's a 0. And page 2 gets linked to by page 4, and that's the only thing that page 4 links to, so that is a 1. If you're following along in the notes, there's a mistake here in the notes, I believe, so that 1 is shifted down when it should be here. Okay. All right, so the next row, I am asking for what is linking to page 3. So page 3 gets linked to by page 1, and as we saw in the previous row, page 1 links to 2 total pages, so that's also a 1/2. So page 3 does get linked to by page 2. So page 3 gets linked to by page 2 in this case, and page 2 links to 2 total as well, so this is 1/2. Okay. Does page 3 link to itself? Yes, it does. Because it has no outbound links, in both cases, the 15% case and the 85% of the time case, it links to itself potentially 1/4 of the time, since there's 4 total web pages, and it is definitely in the pool to be chosen. So it does link to itself, so that's a 1/4. Lastly, does page 4 link to page 3? No, so that's a 0. Okay. All right, page 4. Page 4 only gets linked to by page 2, so here's a 0. Page 4 doesn't link to itself, so there's 0. So it gets linked to by page 2, and page 2 has 2 total, so this is 1/2. And page 4 does technically get linked to by page 3 in the same way. And so this is our matrix T. I was just looking, and there's no questions. That's good. So here's our matrix T. So then the corresponding matrix, I don't think I actually have it out, but so the associated steady state vector is the following. So from the notes, this is 0.1347, 0.1919, 0.4572, and 0.2162. Okay, and remember the way that this vector goes when you have this written out here is that the way that you read this is that P sub 1 has PageRank 0.1347. P sub 2 has PageRank 0.1919, and so on. Right. Okay. So I'll let you think about whether it makes sense for piece of 3 to have the highest page rank among those 4 pages. Okay. All right. So a quick check on questions again. The 1/4 and third column, yeah. So the way that this works is because page 3 has no outbound links. And according to the PageRank algorithm, when a page has no outbound links, then the choice is random 100% of the time. So if you end up on page 3, where you go next, where a random web server goes next, is always random. So 15% of the time it's random, and the other 85% of the time it's also random. So it's random in both cases. So both entries are a 1/4. So if you like, right, I could distribute this 1/4 here so that this is 0.15, and technically all these entries are not just one, they're 1/4, but it's just easier to write this. So all these entries are 1/4, and that's because 15% of the time, regardless of where I am, the choice is entirely random. There's 4 total websites, and so the chance that I end up on any given website is 1 in 4, right? It's 1/4. Now, for this 85% of the time case, what happens when you have a web page with no outbound links, since the choice is always random on this page, the column associated with that page, which is the third column here, is always just one. It's just 1/4 here, right? Because 1/4 of the time, this thing links to any given page, even to itself. Okay, so that's the deal with the 1/4 in the third column. Okay, so a word about how to extend this in general. Basically, here's kind of the general process, and then the only thing that's left really is talking about the MATLAB stuff, which, like I said, I will link you all. I'll actually add to the description of this video where you can find the MATLAB code for this in the notes. So general case of an internet within pages. Okay, so if you have an internet within pages, how does this work? When you go to write out your transition matrix, the way that this works is you have 0.15 divided by n, okay, times some n by n matrix of ones, right? So what this is this is 1, 1, 1, 1, 1, and so on. 1 all down the diagonal, 1 everywhere here. Okay, so this is an n by n matrix of nothing but ones. If you like, I can just write a big 1 here. If I write that, maybe you think it's more like the identity matrix. So let's not do that. So maybe I'll make this prettier here. So our transition matrix T is 0.15 over n times matrix that looks something like this. So this is an n by n matrix. Okay. All right. Plus 0.85 times a matrix that consists, it's also an n by n matrix that consists of the following vectors. Call them v sub 1 through v sub n, where v sub I is determined in the following way. So, one, if we'll say if page I has k outbound links, then the jth entry of the vector v sub I is 1 over k if page I has an outbound link to page j and 0 otherwise. Okay. And 2, if page I has no outbound link, then every entry of v sub I is 1 over n. Okay. So you can compare this with the previous example to see that it's exactly followed in that way, right? So let's go back here. Here's my previous example. So my first vector, look at the only entries that are non-zero are in this vector the second and third entry. So why is that? It's because page 1 links to pages 2 and 3. So in the second column, the only entries that are non-zero are the only entries that are non-zero are the third and fourth, and that's because page 2 links to pages 3 and 4. Okay, in the third column, to see how this goes, you might look at it and say, oh, where's that come from? Well, it comes from this part 2 where you are dealing with a page that has no outbound links, whereas page 1 and 2 did have at least one outbound link each. Lastly, page 4 has a single non-zero entry, which is the second entry because that's the only page it links to is page 2. Okay. All right. And so that is the meat of the PageRank algorithm and how it works. So once you understand how to set up these problems, it works exactly like the Markov chain problems we did. In fact, there's even a little mini section. I don't even know if I should call it that. It's like a one paragraph section in the notes that mentions that if you understand how to set this thing up, you don't even have to worry about verifying that one of the eigenvalues is 1. You're guaranteed that if you follow this process, you end up with a transition matrix. And so all you have to do computationally is exactly what you would have done in the best cases when you're dealing with Markov chains. So basically, if you understand how to do the Markov chain calculations, then once you understand how to set up these PageRank problems, then it proceeds in the exact same way. So that's how that goes. And I'm going to work through some more examples of that. Like I said, next week I'll probably do some problem sessions where I work through those things. But that's the idea. So that's how PageRank works. Okay. Now, a couple of maybe I'll start section 9. Probably won't finish it until next week, or actually I may finish it in one of the supplemental lectures I upload over the weekend. I think that's probably what's going to happen. So anyway, on to chapter 9 material. As I've mentioned several times during this semester, this course is kind of weird in that we're going to touch briefly on a bunch of topics rather than focusing in any particular direction. So oftentimes you'll have, for instance, in the case of Markov chains, that allowed us to do both the PageRank algorithm and also the Markov chain analysis itself came from what we did earlier. So many times you're going to have like direct applications of something that we do. Just like when we did least squares, we use least squares in like 3 different sections once we learned it. So So that's kind of the general idea. So what I want to talk about now then is singular value decomposition. So this is the contents of chapter 9. And basically, the main idea is that you're factoring a matrix. So the main idea is factoring, put that in quotes, a matrix in a convenient way. So you've already seen ways in which you can factor a matrix in a nice way. So one is diagonalization, right? So quick example. Diagonalizable matrices are, say, nicely factorable. Right? So what was the idea behind a diagonalizable matrix? Well, it's that you had your diagonalizable matrix A here, some invertible matrix P, and you might even remember where the P came from, and then you had a diagonal D. Now, diagonalizing doesn't necessarily, that's not really going to feature too heavily here. This is a totally different process, but I'm just giving an example of factoring matrices. So you have matrix A is diagonalizable if it is, you might remember that if you have two matrices related in this way, this is called matrix A and D being conjugate to one another. So if they're related in this way, you would say that they are similar, right? And so another way to read this is A is similar to D, or read out A is similar to D. And the whole benefit of doing this was that you, by diagonalizing a matrix, what you did was you took computations that you wanted to do using some generic matrix that was diagonalizable, and you did it instead in some way on a diagonal matrix associated to A. And of course, it being a diagonal matrix is a lot easier to do those computations. Now, you already know where this comes from. If you have a diagonalizable matrix, what's D? D is a diagonal matrix that has the eigenvalues of A on its diagonal repeated, depending on what their multiplicity is. And then what are P? P are the eigenvectors associated, right, in the order that you have dictated in your diagonal matrix D. All right, and so you're no stranger to matrices being factorable in a nice way. So anyway, this is similar. This has a lot of applications. Just quickly, I can prattle off a bunch. So data compression, matrix approximation, pseudo-inverse signal analysis, facial recognition, that kind of thing. So what is singular value decomposition? It's a particular factoring. So definition, the main thing we seek in this chapter for any M by N matrix with real entries. I'll just say real matrix A. The singular value decomposition, which we'll call SVD of A, is a factorization of A as the following. A is equal to U sigma V transpose. Okay. Now, I haven't said anything about U sigma or V transpose. There's absolutely no info right now as to why you would care about this. So I better describe what I mean by this, because presumably using the identity matrices, you could literally write any matrix like that immediately. So then where U is an M by M orthogonal matrix. Don't worry, I will refresh your memory on what this means. So use an M by M orthogonal matrix. Sigma is an M by N rectangular diagonal matrix. That might be a new term, but with a little bit of imagination you can probably guess what that is. And then next, V is an N by N orthogonal matrix. Okay. Now, orthogonal matrices are particularly nice. I'll give those definitions in just a second. But then what is this saying? So that I don't have to write it again here. Okay, so singular value decomposition of a matrix is me being able to write a matrix in the following way. It's U sigma V transpose. You might be able to recall some linear algebra facts that allows you to relate this expression to the expression here in kind of a direct way. In fact, this is a more general thing. Okay, so looking at this, orthogonal matrices are particularly nice. They're actually really, really nice. So there's a couple of ways in which this thing is like a generalized diagonalizability. One, for diagonal matrices, I had to have P be the same matrix here and here, right? So I had P and P inverse here, but P was a single matrix. Whereas here I have U and V. Now U and V are orthogonal, which was really, really nice. But anyway, U and V are potentially different matrices here, the way I have it written. And sigma is a rectangular diagonal matrix, which is not quite a diagonal matrix because a diagonal matrix has to be square. Right? The definition of a diagonal matrix is that it is square. So what is a rectangular diagonal matrix? It's exactly what you think it is. It is a rectangular diagonal matrix, meaning that it's like a rectangular matrix that badly wants to be diagonal, but because it might have too many columns or too many rows, it can't be. But the good news is those extra columns or rows are filled with nothing but zeros. Okay, so I'm going to write that out so that I'm not on shaky ground. So what's the definition? So first let's define orthogonal matrix. So an orthogonal matrix is a matrix whose columns form an orthonormal basis for Rm in this case, or Rn in the case of V. So also note U and V don't even need to be the same size. In fact, in general, they won't be. So what is this thing? So an N by N matrix is orthogonal if its columns are unit vectors that are pairwise orthogonal. Meaning all of them are orthogonal to each other. Okay, note this is equivalent to saying that the columns form an orthonormal because the column vectors are unit vectors, form an orthonormal basis for, since it's an n by n matrix, this is Rn. Okay. All right. So that's what an orthogonal matrix is. A quick definition of the other term here. It's a little confusing. So rectangular diagonal matrix. So what is a rectangular diagonal matrix? maybe rather than write it out, I'm just gonna give a couple of examples. You can read the description. So the point is that the only non-zero entries that are allowed are on what would be the diagonal if this was a square matrix. Okay, so what's a rectangular diagonal matrix? Let's say 1, 2, 3, and the rest of these are zeros. That is a rectangular diagonal matrix. Let's have another one. Let's do 4, 5, 6. It's another example. So a quick way of saying this is only non-zero entries. Maybe I should phrase this slightly differently because then it makes it sound like something that's not quite saying. So the only non-zero entries must occur on the diagonal, i.e. at position 1, 1, 2, 2, 3, 3, and so on, i.e. A sub I, right? Those are the only entries in the matrix that can be non-zero. All right. Doesn't mean that those matrices are non-zero. It's just that those are the only places where non-zero entries can happen. Remember, there's a very, very annoying fact you're probably tortured with when you were asked a bunch of questions that were true, false, when you first took 240 or 461. You were probably asked a bunch of true, false questions about something like, any diagonal matrix is invertible or something stupid like that. But remember that the zero matrix is diagonal, right? It is a diagonal matrix because off its diagonal, everything is zero. And that's the only requirement. So similarly, if I took either of these matrices and I filled them with nothing but zeros, both of those would also be rectangular diagonal matrices. So rectangular diagonal matrices, much like diagonal matrices, are defined in terms of there being nothing but zeros off the diagonal. So long as that's satisfied, it doesn't really matter what's on the diagonal. So what's more important in a diagonal, or for a matrix being a diagonal matrix of any type, is what's not on the diagonal, not what's on it. Okay. All right. So then how does this work? So there's a big theorem. I'm not going to prove any of it. I'm just going to state it to you as fact. But there's a theorem that informs how we're going to do this factorization. So question: how do we find the SVD for a given matrix A? Okay, and or at least a partial answer. So first, a theorem that's going to help us answer this. So here's the following theorem. So this is like theorem 9 point something in your notes. So the following are true. Okay, so 1, an n by n symmetric matrix has n unit eigenvectors all perpendicular to each other. I.e., the matrix containing them or I should say composed of them, is an orthogonal matrix. Okay. You might recall this when you first took 240 or 461. This was the bit that was done near the very end of the semester. It was something being orthogonally diagonalizable. Okay, this was a special thing. Okay, so symmetric matrices are really, really, really nice in that way. For any matrix A, we've actually seen this before. I think this was one of your exercises, actually. The matrices A transpose A and A transpose are symmetric. What does it mean when a matrix is symmetric? So, a reminder, A is symmetric means, or rather is exactly, means that A transpose is equal to A. So taking a matrix and transposing it leaves you with a matrix that's identical to the one you started with, right? That's what it means to be symmetric. So both of these are symmetric, and the reason they're symmetric is easy to see. You just take their transpose, and remember that transpose takes a product of matrices and flips it, right? And since it flips a product of matrices, you can just quickly see. If you take the transpose of A transpose A, you get A transpose A. Okay. And similarly for this other one. So both of those are symmetric. So you might see where this is going. So third bit, for any matrix A, the matrices A transpose A and A transpose share the same non-zero eigenvalues. Okay, you might try to think about why this is. Remember, go back to the very first day you heard about eigenvalues and how you find them. So you find them with the characteristic polynomial for a matrix. So you might want to consider what is the characteristic polynomial for these two matrices. Okay, so there's actually a more direct way than that. But anyway, lastly, for any matrix A, the eigenvalues of A transpose A and A transpose are all non-negative. Okay. All right. So here's the setup. Okay. So then how do I compute? How does this help me compute the singular value decomposition? So this is, you might guess that I'm going to take my matrix A and I'm going to form these matrices that are symmetric and use number one to tell me some nice stuff about them, right? Namely that if I can find their eigenvectors, well, normalizing them, what do I get? I get an orthogonal matrix containing the eigenvectors, which is actually similar in process to how I diagonalized a matrix, right? The only thing now is that the sizes don't actually have to match up the way they do for diagonalization. So how does this go? So how to compute the singular value decomposition of A. How does this go? So remember, what we're looking for is factorization of A as a product of matrices U, sigma, V transpose. Okay, so here's how we do it. So to find U, first of all, U is m by m, right? And columns of U are an orthonormal basis of Rm consisting of the unit eigenvectors of A transpose. Okay. Now, a couple of things. If you found an eigenvector, making it unit is no problem at all, because you take an eigenvector, multiply it by a scalar, that's still guaranteed to be an eigenvector. And furthermore, remember that we don't consider the zero vector an eigenvector for a matrix, and so we don't have to worry about, that's the only vector we can't normalize, right? So we don't have to worry about anything that might come out of that. So these are the left singular vectors of A. Okay. The fact that this works out nicely is a result of parts 1 and 2 of that theorem that I just wrote out, right? So there's my theorem. Okay. So that's how to find U, and these are called the left singular vectors. Okay. So to find sigma, I'll put underlines here. Okay, how do I find sigma? So sigma is an m by n matrix. The non-zero diagonal entries of sigma are called the singular values, which is where SVD gets its name, called the singular values of A, and these are the square roots of the shared, because they agree by part 3 of the previous theorem, eigenvalues of A transpose A and A transpose. Okay. All right. Lastly, to find V, so V is n by n. You might have already guessed what it is just from the first two. So columns of V are an orthonormal basis of Rn consisting of the unit eigenvectors. What's it going to be? This was the unit eigenvectors of A transpose, which is an m by m matrix. This is the unit eigenvectors of A transpose A. Okay, these are the right singular values. Or sorry, right singular vectors. Okay. Now, there's a note here that says that typically the singular values are arranged in non-increasing order. This is similar to how diagonalization worked. So if you remember, there was no requirement that you order the eigenvalues of when you're diagonalizing a matrix. There was no requirement that you ordered the eigenvalues in any particular way. So you didn't even have to group the eigenvalues that had multiplicity greater than 1 together, right? So if you had a double, like an eigenvalue with multiplicity 2, say 1, so 1, 1, you didn't even have to have it read off 1, 1. You could have broken those values up and had them separated along the diagonal. The only thing that's important is that you then rearrange the corresponding vectors in P when you're diagonalizing a matrix. As long as you got the order of the columns of P correctly, you could actually arrange those eigenvalues any way you want to. The same thing is true here. So yeah, it says that typically they're arranged in non-increasing order, but however you arrange them, you just have to make sure that the corresponding vectors in U and V are altered to match that order. That's why it's good to just keep it simple. So anyway, I'm not going to do an example now. I'll save that till either, like I said, one of the supplemental lectures I put up over the weekend or maybe next week. So I think that's pretty much all I wanted to say for today. So I think there's no more questions. That's fine. So I will finish this stuff. If I don't finish it over the weekend, when I post a lecture at some point before Tuesday, I'll finish up next time. So anyway, I'll keep you all posted, and pretty much everything should be like absolutely set in stone by next Tuesday. So anyway, I will see you all later.